Okay, welcome to what's now ending up as lecture 11 of your refrigeration module. Here we're going to discuss, although the title is called refrigeration gauges, we're going to discuss the pressure enthalpy chart and the temperature enthalpy chart, applying it to a practical situation to calculate subcooling or superheating or saturated values. Okay, so let's get on with it. To be able to understand what we're going to do now, it's a good idea to go and revise lecture 2, lecture 3, lecture 4 and lecture 5 presentations. So just quickly to recap, lecture 2, ice, water and steam lecture, was the experiment where we melt ice, we boil some water and we make some steam. So in that particular lecture, the temperature enthalpy chart principles was presented, and from that lecture we note that sensible heat causes a temperature change, latent heat energy transfer causes a change of phase, that a substance can be called subcooled, saturated or superheated depending on its temperature. From lecture 3, where we looked at the vapor compression system of a refrigeration system, and of importance was the diagram with the 4 main components, the pipe diagram showing the direction of flow. So also on that diagram was presented the processes going on in the condenser and the evaporator. We also can divide that into the high pressure side and the low pressure side. That'll come in later when you are talking pressure gauges and pressures in the system. And then we have heat energy transfer that either causes a change of temperature or a change of phase in the refrigeration system. And then in lecture 4, the vapor compression cycle, here we actually took the cycle and plotted it on a pressure enthalpy chart. And from this pressure enthalpy chart, we can see the different heat energy transfers taking place in the actual cycle. Also, a previous lecture, lecture number 5 on refrigerants, introduced the concept of pressure-temperature relationships. Each refrigerant has basically got a unique pressure-temperature relationship, and this pressure-temperature relationship is important for a refrigeration technician. He needs to know what refrigerant is in the system, and he needs access to data of the pressure-temperature relationship, so a vapor table as we would call it. So from that pressure-temperature relationship we can notice that if the pressure changes, a corresponding temperature change will occur. Also, if the temperature changes in the system, a corresponding pressure change will occur. So we can also see from the above that using the pressure-temperature relationship we can identify a refrigerant. We can use the pressures to predict the working temperatures, and we can use the working temperatures, for example the ambient temperature cooling a condenser. We could predict what the expected working pressure in the condenser is. For this to work though, the refrigerant must be a pure refrigerant, it must not be contaminated. The refrigerant must be contained in a system or a cylinder, and it must be a saturated mixture. Okay, here we have an example of a refrigerant vapor table published by a manufacturer. So manufacturers produce these chemical refrigerants, and then part of the data and safety data sheets, they produce these tables. So these tables are of importance to refrigeration system designers and developers, also the installers, and then maintenance technicians need to know if the system is actually working the way it was designed to work. So we can identify the chart, the type of refrigerant, by looking at the R number. In this case we see a 134A. And then you can also see that there are two main columns. The page is divided in half, and in the left half is a set of columns that is then repeated in the right half. So we start at some low pressure, low temperature on the left top, and we work our way down the first column and then up again to the second column, down to the end of the second column, where we will end up at some high pressure, high temperature. Okay, taking a little bit closer look at the actual columns, we can see that this is a (134A) refrigerant. It is Solkane, Solkane being the manufacturer's name of the refrigerant. So they call their refrigerant Solkane 134A. When a technician wants to buy refrigerant, he will go to the supplier and he will ask for R134A. Whatever manufacturer has supplied the supplier, that's what he will get. So the next thing we need to see in the chart is the temperature column. So you can see here the temperature is in degrees Celsius, and it starts at a -50 temperature and it works its way down, getting warmer. We come across to the other column, we can see the temperature again, and it starts at +30 and it works its way down, getting warmer. The next column of importance is the pressure column. You could see the pressure column here. It starts at the low pressure and the numbers increase as the pressures increase as we go down the columns. Again, this part of the chart, the pressure starts at a particular number and it increases as we go down. Of importance to note is that these are absolute pressures. So the pressures are an absolute value. That means that you cannot take the number you see on a pressure gauge and go to the chart. You have to modify the pressure gauge to make it an absolute pressure. We will look at this later on. The rest of the columns are other informations that would be used by designers and system installers and so on. So of interest now would be the volume columns. So this one being the volume of liquid, and you can see the unit is decimeters cubed, and the numbers start with a 0.6, a decimeter cubed being a liter. And then this next column here being a volume of vapor, also decimeters cubed, but you can see the number is fairly huge. So we have 0.6 liters in volume of liquid, and then we have 586 liters in the volume of the vapor. So this just means that a little bit of liquid makes a large volume of vapor. So you can get an idea now of the different diameters of the pipes in a refrigeration system. Okay, so let's take a closer look at these columns. So the pressure temperature charts. The temperature column T in degrees Celsius mentioned already. You can see the units, and then the pressure column in bar. So our gauges may not always be bar. They can be kPa, they can be kilograms per centimeter squared, and some imperial units, psi, pounds per square inch. So it's going to be beneficial for you to be able to convert between different pressure units. Okay, so the main point here being pressure is in absolute pressures. So the temperature decreases as the pressure decreases. What you can see here is as we go down this column, the pressure is decreasing, but you see, sorry, the pressure is increasing and the temperature is increasing. Don't get confused by the negative numbers. Alright, so although the number is getting smaller, we are negative numbers, it means it's getting warmer. Alright, so moving down is warmer, moving up will be colder. In the pressure column, moving down the pressure column is an increase in pressure. Moving up the pressure column is a decrease in pressure. So looking down here, we can now see that there is a pressure change will cause a temperature change, and a temperature change will cause a pressure change in a closed system. So if the pressure goes up, the temperature goes up. If the pressure goes down, the temperature goes down. Okay, so it's changing in sympathy. Right, let's look at the next slide. Okay, so revisiting chapter 4 of your student notes, where we looked at the high pressure side and the low pressure side, and applied the notes from chapter 3, the ice, water and steam. If we look at chapter 4 of your notes, 4.6, you can see we are having a look at the components diagram, the 4 components diagram, and then we have the temperature enthalpy chart, corresponding temperature enthalpy chart. So the condenser is on the high pressure side, and in the condenser we have condensation taking place. Alright, so this would be a vapor changing to a liquid. So to be able to use this temperature enthalpy chart practically, we need to plot our compressor. So our compressor would be over here. In this diagram, the condenser itself, you just change the temperature here, the color. The condenser would be in this particular region over here, and that would be the place where the condensation would be taking place. And if we drop the lines down here, if we drop these lines down here, then we can see that this region over here is where we see, good grief, we see the latent heat transfer taking place, and that would result in a change of phase. So we have our vapor leaving the compressor, we're passing this way down the chart, we're going through the actual condenser, and then we're coming out subcooled. Okay, so we reach a certain point over here, so this point over there being the boiling point. Okay, sorry, condensation point. So there's our I'm having a struggle with this computer. Condensation point. Oh, that's a waste of time. Okay, so that's the condensation point. So condensation starts, vapor turns to liquid, and then at the end of the change of phase, where we have 100% liquid, if we are still removing heat energy, then we can cause the temperature of the refrigerant to cool down. Okay, so there was a major removal of heat energy in the latent heat phase in this area, and then we come to this area where we are removing heat energy. Jesus, making a mess. And we go down and we have subcooling taking place. So the subcooling being the temperature is less than the saturation temperature. Of course, this is all occurring at the high pressure. So whatever the high pressure is in the system, we have that high pressure corresponding to the saturation temperature. Okay, so I know the diagram looks a mess, but this is what I've got to work with at the moment. Right. The low pressure side is exactly the same concept, but applied in the opposite way. Okay, so the high pressure side, high temperature, low pressure side, low temperature. So in the high pressure side, we're moving from the compressor through the condenser to the expansion device. In the low pressure side, we're moving from the expansion device, metering device, through the evaporator back to the compressor. So our evaporator in this particular case will be over here. Okay, so just like in the previous slide where we discussed the condenser, the main way that heat energy is transferred out of a refrigeration system or in a refrigeration system is here. This change in temperature, change in heat energy transfer, latent heat energy transfer. Okay, where we have condensation or evaporation taking place. So on this particular system, our compressor is still over here. Okay, so there is the compressor, and the compressor is taking refrigerant from the low pressure side. So we are on the low pressure side, and the low pressure is having a relationship with the low temperature or the saturation temperature inside the evaporator. Okay, so our expansion device would be literally over there. Let me change the color a bit to make it a bit more visible. Okay, so it differentiated a bit. There we go. All right, so that's our TXV is over there, and that is having high pressure refrigerant, which is subcooled, arriving, passing through the expansion valve, and then leaving the expansion device as a saturated mixture. So the saturated mixture we can see is in this region over here, and that saturated mixture is boiling, evaporating. Evaporation is the process. So as the refrigerant passes through the evaporator, the liquid changes to a vapor, absorbing a whole bunch of heat energy. Okay, and whatever amount of refrigerant is passing through, we would like it to be 100% vapor by the time it leaves the compressor. Okay, so we would prefer that superheated vapor arrives at the compressor. And if we just quickly plot down here, we can see that superheat allows us to transfer or absorb a little bit more heat energy into the refrigerant. And if we draw a line across there, we can see our superheat value is warmer than the saturation temperature. So we are starting to build an understanding of using the theory and these temperature enthalpy charts to diagnose or to understand the working of a refrigeration system. Okay, so we are going from a subcooled liquid into the expansion device, metering device, and then through the metering device we are passing a saturated mixture into the evaporator coils, and hopefully all the refrigerant liquid is evaporated and superheated vapor arrives at the compressor's suction ports.